Hello. So before we go ahead, let us now derive the wave equation that arises from the Maxwell's equations. You would see that it was Maxwell's correction to the Ampere's law that actually led to the realization of the wave-like solution for electromagnetic waves. What I want to look at first is the two time-dependent equations that we have. That is, first is the Faraday's law, which is del cross E is minus dou B over dou T. And the second equation is the Ampere's law, which is del cross H is dou D by dou T. So I have made a few approximations here. Then let me write those down. So the first approximation I'm making is we are in a source free region. That is my rho free, which is free charge density, and J free, which is my free current density. Both of these quantities are zero. This is the first approximation. And the second approximation which I want to make is that my permittivity and permeability, the electric and the magnetic properties that characterize the medium, both of these are uniform in space. So given these two approximations, we will go ahead and derive the wave equation. This equation, of course, will be valid for vacuum, for example, which is wherein you get epsilon becomes epsilon naught and mu becomes mu naught. Uh, it is also valid in uniform dielectric media, for example, a piece of glass or any transparent uniform media. It is widely applicable. So even in atmosphere, if one doesn't worry about local variations of the atmosphere, this would remain valid. So now let me take the first equation and take the curl of it. So I'm looking at del cross E on the left hand side. On the right hand side, I have got the curl of minus dou B over dou T. I have to quickly realize here that space and time are independent quantities, and these operators are independent of each other. So I can interchange the sequence in which these operations happen. So I can write this equivalently as minus dou by dou T of del cross B. Now you will see that if I want to rewrite this equation in terms of the electric field itself, I have to use the second equation, which is the Ampere's law, to go ahead. So let me quickly uh, recall for you as an aside what we have seen earlier in our previous lecture, which is the relationships between B and H as well as D and E. So you know that the B field is simply mu naught H plus the magnetization. For a linear medium, I can write this as 1 plus susceptibility of the magnetic kind, that is chi m times H, right? And this quantity is what we call as mu relative, or in other words, succinctly, this is just mu times H. This is the first aside. The second aside is what again you know, which is got to do with the displacement vector. So D is epsilon naught E plus the polarization. And remember, for linear response, we wrote down polarization as epsilon naught times susceptibility chi times E. So I can write down my D as epsilon naught 1 plus chi electric times E, which in other words is akin to the top equation, epsilon times E. And when I made these approximations, I made the approximation on this epsilon, or effectively on epsilon relative, or the susceptibility stating that these are uniform in space. Right. So let me look at the right hand side of this equation and continue from there. So I have got basically minus dou by dou t, and del cross B, I can replace my H as B by mu. So I can write this out as mu times dou D by dou T, which in other words can be written as minus epsilon times mu dou square E by dou T square. So I have reduced my equations back all in terms of the electric field. You realize that it is this going back and forth B between B and H as well as D and E arises precisely because of this displacement current factor which Maxwell put in and corrected the Ampere's law. Without this term, we would not have essentially the wave equation. Right. So now let's look at the left hand side. I can replace my del cross E as the gradient of the divergence of E minus Laplacian square, we call it del square E, which is minus epsilon mu dou square E over dou T square. Again, I note that I have already made the assumption, which is that if I go back to now the Gauss's law, which is del dot D is rho free. Now remember that we already made the approximation that we are in the source free region. So this comes out to be del dot epsilon times E, which by the way, because epsilon is uniform in space, the del operator does not operate on it. So this can as well be written as epsilon times del dot E, which is equal to 0, which simply implies that del dot E is 0. This condition is called the transversality condition, and I will plug it in here and thus obtain the final wave equation, which is del square E equals epsilon mu times dou square E over dou T square. Now I'd like you to look at this wave equation and identify for yourself what is the velocity of this wave in this medium. So if you do that, you will see that this epsilon mu factor can be identified as the 1 over velocity square factor, which arises in typical wave equations. In other words, my V is 1 over square root epsilon mu, which I will rewrite as, I'll open up the dependencies, epsilon naught times epsilon relative, mu naught times mu relative, which is simply 1 over epsilon naught mu naught times 1 over epsilon relative mu relative. So by the way, it is this factor which 1 over square root of epsilon naught mu naught, which Maxwell derived and found that this is precisely the speed of light, which is c, which was already measured then. It was a measured quantity, and hence one can write down the velocity as c by square root of epsilon relative mu relative, and this is what is the definition of the refractive index, which is the ratio of the speeds between the medium and the vacuum. So the velocity in the medium is given as c by n, where n is the refractive index. Now let me repeat a note I had made earlier, which is that mu relative is 1 for all optical frequencies, right? This is for all naturally occurring media. At optical frequencies, there is no magnetic response, hence mu relative is 1, and hence the refractive index itself can be written as simply square root of epsilon relative, or in other words, 1 plus chi electric, which is the susceptibility. So this is essentially what is the wave equation and the corresponding velocity with which electromagnetic waves move within such a medium. By the way, this velocity v that we are talking about is called the phase velocity. There are multiple other velocities that one can talk of. For example, one can talk about the group velocity, one can talk about the velocity with which energy is transported, and so on. I will not get into that. That in itself is an extensive discussion, which we will not get into. One of the important considerations is that my refractive index n itself can be complex. It can be n real plus I times n imaginary. And we will get into the details of this refractive index slightly later. But as I told you, the imaginary part will dictate something called absorption, and that can easily be accommodated within such a description of the electromagnetic fields inside a medium.